Usually it's an hour, around an hour, but yesterday it went a bit more. I thought it was gonna be shorter, but it went a bit longer. Yeah.
We always say that.
Anyways, today is our last day of our topic 5 review. We only have less than a week of class left. Did you know that next class is our last class?
Yeah.
Because I don't see you on Wednesday.
Yeah, Wednesday we don't have.
Wednesday we don't have, yeah, so it's quite crazy. So, good luck to you all.
Welcome to class, don't want you.
Yes. So come here.
We can still come back, right?
Yeah, I'll close my door and just.
I'm breaking, who cares?
Yeah.
Suspension doesn't.
Anyways, I'll open the doors to Alina because she got me water.
I need help.
Anyway, so today we'll go through the topics. As always, I've divided them into chapters. I think I put them into big 5 chapters. It comes with limit, differentiation, integrals, differential equations, and Maclaurin series. So the first one, why is it red? Goes at limit, differentiation. We also have the integral, lagging already, integrals. And then we have the differential equation. And finally, the Maclaurin series. Okay, so let's start with the easy ones, the limits. So limit is kind of like the fundamental understanding of what differentiation is. But basically what we do is we write the notation as a limit as, for example, x approaches 0. That approaches 0 could be like 0 or infinity or anything of a function that we choose. Okay? So sometimes taking the limit as x approaches 0 is just easy, right? For example, if you have limit as x goes to 2, let's say x squared, then it's just going to be, well, if it approaches 2, my x squared will also approach 4. Right? So that's pretty easy. Just a couple of things we need to note is that for limits, we also have the concept of direction. Right? So for example, let's say we have a limit as x approaches 2. We have a function of something like, let's say, 2x plus 5 divided by x minus 2, let's say. So in this case, what happens if I approach 2x plus 5 over x minus 2 if x approaches 2? Right? Just by looking at the graph of it, this is a rational function, and we have a vertical asymptote at x equals 2, right? So that would be do not exist, because we know that the graph, the function f of x does not exist when x equals 2. However, if you take a specific direction, then the story kind of is different. If you say that limit as x goes to 2 from the negative side, so it means that the graph goes from the left and you go towards 2. So from like 1.5, 1.9, 1.99 and such towards this number. Of course, it's going to go down to like negative infinity, which is also the same as do not exist. But we see how it's kind of different, right? The concept is different. And of course, if I take this to limit as x goes to 2 from positive side, which then we can say that it goes from the right hand side. It's probably going upwards. Let's go upwards.
Yes.
I don't know. I don't know what the graph of 2x plus 5 over x minus 2 looks like, but assuming that, it's going to be a positive infinity, which is still do not exist. But still, we can see how the direction kind of matters sometimes. Right? So sometimes we could have a graph that's given to you that goes like this, and then you have a dot here, and then goes like this, for example. Then the direction here definitely does matter, right? As if that's 2 here, let's say this is 4, and let's say this is 1, then we can say that limit as x goes to 2 from the negative side, the limit is 4. Whereas if it comes to the right hand side, it's going to be 1.
So does the limit exist? Doesn't.
So in this case, the limit does not exist, just at 2. But if you go from negative side, it's 4. From the positive side, it's 1.
But the overall limit would.
Overall limit does not exist.
Okay.
Yeah. It's also not continuous. It's also not differentiable, but that's fine for now. So I was right. Thank you. So we talk about the direction of the limit. We also have to talk about the idea of the derivation from the first principle. So if you check the formula booklets, we have the derivative of f of x from the first principles, right? So here we actually see where the limit, where the idea of differentiation comes in from taking the limit. So we have f prime of x is defined as limit as h goes to 0, the limit of f of x plus h minus f of x divided by h. So this is the first principle. So if you ever want to find the derivative of a function with more, step-by-step, the fundamental guideline, then you follow the first principles. Just by looking at this, what do you think? Will this limit be existence? Not in the first sight, right? Because h goes to 0, so that we're dividing by 0, so that it doesn't make sense. However, in the process of this work, if you simplify the f of x plus h minus f of x, usually, in most cases, the h will cancel out on the bottom, so get rid of the denominator h. Okay. So for this case, we can avoid that by simplification and factoring out. But also we have some case where it's just not possible, right? So then we have the method of doing the L'Hopital's rule. L'Hopital's rule is helpful if you want to take a limit of something but you can't, then you take an alternative route, right? So let's say we want to find the limit as x goes to 0 of f of x over g of x. Okay. You want to take a limit, but let's say this is difficult because both f of x and g of x goes to 0 when x goes to 0. Let's say we have like sine of x over x, for example. Or we could also have a case where both goes to infinity or whatever, right? Then we say that, hey, let's see you on the next round. So we kind of go on the overtime match, and we take the limit as x goes to 0, but this time we take a derivative of f of x over a derivative of g of x. And then we take a limit as x goes to 0. And then we can repeat this process many more times if you need to ultimately make sure that hopefully my denominator does not go to 0.
Right. Even if, okay, now I get it. The second derivative works for the third.
Yeah, second derivative works, third derivative works, and such.
Smart.
Okay. Do you have the L'Hopital's rule in the form booklets?
Yeah. Wait, I don't think so. I don't think so.
Do you? I don't think so.
It's a common sense, right?
It's common sense. Not really, but it is common sense.
Actually,
Yeah,
yes.
sadly.
Just need to see.
Anyway, so this is the method of the L'Hopital's rule. Any questions about the limit? It's kind of a
Need
fun.
to determine if a function is continuous from calculations.
Probably not. Like if you have.
Because the textbook, there's a lot of questions where it asks you, determine if this function is continuous or not.
Yeah, there was a chapter of continuous, right?
Oh, okay.
Yeah, continuability. So maybe it's because of that. Continuability and the differentiability and such, they're kind of together, or the limit exists, they go together more conceptually. That's for the building concepts. So I don't think they're directly useful for solving questions. Like they wouldn't ask hey, is this continuous? Maybe if they want to do that, they'll probably show you a graph and then ask you if it's continuous, if it's differentiable, if the limit exists. Or you will have access to the calculator, so you can just graph the function and see it yourself. Yeah.
For paper 3s and stuff, there are a lot of there were a couple questions where they would put conditions and find this constant parameters value where would they be able to say where this
Where
graph is not
the f of x
continuous?
is continuous, right?
Yeah. or
Then
not continuous.
right. So let's just quickly touch the idea of the continuous and the differentiability. So first, the limit has to exist if the limit from the left to right is the same.
Yeah.
That's where that's where the statement of limit exists comes in. Also, it's differentiable. Let's talk about continuous. Continuous is it's continuous when the limit exists, and also it's differentiable. So if the points have to be connected, at the point, and then it shouldn't radically change the shape, right? So let's say even if you have like points like, let's say a graph. Let's say you have a function like going like this, and then going like this. Let's say these 2 points are connected, so the limit does exist, but then it's not differentiable because the shape kind of radically changes. So for most cases, I think I said that wrong. I think I mixed up with the differentiable and continuous.
This
I
is
think
continuous.
Yeah, this is continuous. Sorry, my bad. So first,
Continuous.
the limit exists if they're equal. Continuous if the points are connected to each other. And then differentiable if it's continuous and the limit exists.
So the limit exists for this one.
Limit exists for this one.
It's continuous.
It's continuous.
But it's not differentiable.
It's not differentiable. Differentiable,
I think it's called like a cusp.
sorry.
when it
Let's
has
do
like
a,
sharp-
a quick back to our notes. Chapter 15. I think I had like a table, right? Limit exists if the left and right exist.
Limit approaching infinity does not exist, right? Right?
So continuous if the limit exists and the values are the same, right? That's continuity. And differentiability, I think we had it in the later chapters. Sorry about that. Oh, differentiable is when the left-hand derivative and the right-hand derivative are the same. Okay, so now I remember. Let's go back to example. So in this case, this graph, this function, is the limit exists at that point. It's continuous because they're equal and the limits are the same as well. And it's not differentiable because if you try to find the derivative of that point from the left-hand side and the derivative of the right-hand side are different. Okay? So differentiable only when the graph has kind of a smooth pathway, you could say. Sorry for the confusion. Yeah.
So for the limits, if the limit approaches infinity, it doesn't exist.
No.
Okay. Because I was thinking if it's an absolute function, even if there is a vertical asymptote, they're both going to go to positive infinity, right? So would the limit be on that vertical asymptote infinity? But I guess that wouldn't exist anyways because it's infinity.
What do you want to say?
Yeah, cusp.
Just if there's a function that has a
Yeah.
vertical asymptote, but we take like the absolute value of the fx.
Oh yeah, okay.
So
Yeah.
So the
So even if they both go together to the top, yeah, we still that's not exist.
okay.
Although it goes positive infinity, positive infinity.
Yeah.
Yeah. Can I write the limit exist? The limit exist is when the limit as x goes to a from negative is equal to the limit as x goes to a positive. Right? And continuous is when limit exists and the f of next and differentiable is the condition was continuous, right? Yeah, continuous. And the derivative of d of x at f of x are same in both sides. So if you take the limit from the left hand side, if you take the limit from the right hand side, they're still the same. Okay.
Do we need to memorize those things like as x approaches 0 of sine x over x equals 1.
So you didn't have to memorize that because now we have the L'Hopital's rule. We can solve it easily. Yeah. That's a typical example of using the L'Hopital's rule because as x goes to 0, sine x goes to 0, x goes to 0, that's 0 goes to 0. Right?
Yeah.
So that's when you use L'Hopital's rule. Right. Anything else? Let's move on. Let's go to chapter 2,
Keep going.
differentiation.
Yeah.
So, as we talked about the first principles of calculus. We define what f prime of x is. So we have multiple representations, right? So we can either write it as d over dx of f of x. We can also write it as f prime of x. What else do we do? Sometimes we do like, although not usually, we do like f with a dot above. That's a single derivative. You put two dots, that's double derivative. It's kind of messed up. But mostly we use these two notations. Okay. Let's talk about the standard derivatives. So we already have access to most of the derivatives of regular functions like sine of x, the cosine of x, e to the power of x, and also, of course, we have the polynomials, derivative of x power of n. Take that as n x power of n minus 1. And we have some more in the HL topics. In the actual exam, I've seen they're kind of together, so you don't have to look through various parts. I'll show it to you on Monday. We also have a bit more information: tan x, secant x, cosecant x, and cotangent x, and blah 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 as well. Okay. So whenever you're trying to derive something, differentiate something, check the formula, right? And see if there's already one for you, so you don't have to go around like, okay, how do I differentiate arcsine of x? That's a bit of pain, right? So make sure you use the formula as much as possible. Other than the standard derivatives, let's talk about the tangent line. So what is a tangent line? Well, if you find the differentiation of f of x at a point x equals a, let's say, then we say that differentiation, or f prime of a, is equivalent of finding the gradient at x equals a, right? So then you find the gradient of a line from that differentiation, and then we also find, after you find that the point, we can easily find the y value of that point, right? So you do f of a to find the y value, and then you use the point gradient form to find the tangent line, right? Which goes like y minus y1 equals m x minus x1. That's an easiest way to find the tangent line of a specific point. You find the differentiation of that point, and then you also find the f of a, and then you use the point gradient form. Right? If you ever want to find a normal line, so you do a similar thing, except after you find the gradient, you multiply by the negative 1 over that to find the perpendicular gradient.
We multiply the gradient by negative.
You multiply, so if you, let's say the gradient turns out to be, let's say 2,
Yeah.
then the normal line, the perpendicular line will be negative 1 over 2.
Okay.
Negative 1 over the gradient.
So this is perpendicular to the graph.
Yeah,
Right.
The negative reciprocal?
negative reciprocal, that's right.
Smart guy.
Anyway, so that's the tangent line thing. We also have to talk about the second derivative. So this is kind of simple enough too, but if you ever want to do this multiple times, then we represent it as a d squared f over dx squared, something like this. We can also represent it as f double prime of x. We can also represent it as f with 2 dots. You can ignore the last parts. That's unnecessary. I've seen an IA paper who uses that, but anyways. So that's the idea of a second derivative. So what does that mean? We just take the derivative and then you just do it one more time. Okay. That's pretty simple. Product rule, quotient rule, chain rule. So if you ever want to differentiate some weird shapes, for example, let's say you're trying to differentiate something like, let's say, x sine x, let's say. Right? So you see this, and then you think of this, hey, this is a product of two different functions, right? This is you can represent it as d over dx of u dot v, where u and v are both functions of x. So then you take the formula booklet out. I think it goes like u prime v plus u v prime. I think of it as you take terms, right? You differentiate the first apart, and then you do it again, but this time the next person do it. So that's a product rule. We also have the quotient rule. If you ever have a case where you have u over v, if you want to differentiate this, then you do the similar thing. I always like to check the formula booklet for this one because the order does matter. So
Is
for
it easier to use product rule and
on the reciprocal,
yeah?
I think so too, but I don't know. Sometimes it's up to you. I don't stop you from doing that. So I think I'll do the similar thing.
Products and quotients are basically the same thing.
Vu prime minus
U times 1.
uv prime.
Yeah. Use product rule.
They write it vu prime.
Like
That's kind of
U
weird.
times v to the -1.
uv prime. Yeah, I was right. uv prime divided by v squared. That's the quotient rule. And yes, as Alina said, if you want to do a d over dx of u over v, that's equivalent of saying that's u v negative 1, right? So then you can do the derivative of that as a product rule. Sure. And then of course we have to talk about the chain rule. Chain rule is when you have, let's say, f of g of x. So if you have the case of a, what is this called? Composite function, then you use a chain rule. Okay, chain rule.
Look at C answer.
Okay, so that looks like this. Chain rule is basically what you do is you differentiate the outside first, so f prime of g of x, and then you take the inside and then you differentiate that too. I like to think of it as a kangaroo. So if you want to differentiate a kangaroo, you differentiate the mother kangaroo, and then when you differentiate that, the kid is inside is fine, and then you take it outside and you differentiate the kid kangaroo as well. Hopefully you don't laugh in the middle of the exam.
Oh yeah, well,
Yeah.
Mr. E,
Yeah.
for the quotient rule, when we said we can like differentiate it as like
It's like
v
you
to the power of
define it
negative
as
1, don't we need to do a chain rule as well? Since it's 1 over function, so you differentiate that and then you differentiate the functions.
I think what Alina was talking about was let's say it's like d over dx of sine x over x. Let's say.
Okay.
Then we can just think of it as sine of x times x power of negative 1. Then this is going to be cosine of x times x power of negative 1 plus sine of x times x power of negative 2
Yeah.
times negative 1.
Yeah, so you do the chain rule.
Yeah, you do no, it's not a chain. It's a product rule,
Oh, product rule.
but it's a bit simpler, apparently,
Yeah.
according to Alina.
That makes sense.
In some cases, yes,
And
that's
you
true.
only have to remember one rule.
Exactly.
The
Yeah.
product-
No, but
Products.
like if if it's not that simple, if it's like x squared plus 2x, then would the same thing like would it be
Yeah.
hard?
Depends on the scenario. Maybe it will be harder. Yes. So.
Well, I guess, yeah, like if you had a polynomial as your denominator, to make that all to the negative 1,
Yeah.
and then you have to.
That's a bit too much. So it depends on the context, right? Anyways, let's move on. Let's talk about the critical points. So why do we talk about the second derivative? We kind of like just zoom through it, right? Well, what is the meaning of the second derivative? So, well, it's related to our first derivative, and we're related to this critical points. So what are some critical points in our function? The most important parts is the turning point and also the inflection point. I thought you spelled it as inflection with CT, but on the exam it says X, so I don't know. What is the turning point? Turning point is basically the max or min, right? When the graph turns around, right? The graph goes up and then down, or down and then up. Well, what happens at the point? We know this as, hey, that's when the gradient is 0. That's when f prime of x is 0. That's a turning point. An inflection point, however, is when it's not max or min, but when the concave up or down changes.
When did they ever use this in a question?
In the inflection point.
Yeah,
Yeah.
paper three exam we did in class, it had the inflection point. Because it said, for example,
Like find the inflection point?
no, if it said, for example, if the inflection point's gradient is 0 or something, which was weird.
Or you may also have a question where you graph it, you sketch a graph, and then you need to label the inflection.
Oh, yeah, that's.
Also, it's also the matter of understanding that inflection point is when the overall trend is changing, right? So what is this? This is when the second derivative of x is equal to 0. Okay. If it's positive, it's concave up. If it's negative, it's concave down.
Wait, if it's equal to 0, how can it be positive? Huh?
Oh, that's like
No, it's the change.
it's when it changes, right?
Yeah. Well, I understand the positive is concave up and negative is concave down, but
Yeah. At zero, concave up, it becomes concave down.
Yeah.
When it's concave up or
And how do
concave
you
down
figure that
before,
out?
it becomes concave up after.
How do you figure that?
No.
Except double prime x equals 0.
Can you do an example for
That's
the
it.
inflection point?
Can you please like draw a graph and label?
Sure. Okay.
Isn't it when there is no instantaneous change in the slope of the graph?
No, there's also some stationary inflection points and stuff like that.
I'm spazzing out.
I said it's like the midpoint. where
Let's say I have
it's-
a weird function like this.
Yeah.
Then first of all, we have the turning point, right? Easiest ones.
Yeah.
That's our turning point. That's when the f prime of x is equal to 0,
Yeah.
my maximum. And then I also noticed that at some point, my graph overall is concave up, but also at some point, my graph is overall is concave down. Right? So where is that? My graph is concave up, probably until there, right? And then after that point, it's also concave down, right? So in this part, this is up, and this part is down. You see it? So then, at that point, is when things are changing.
So the line would be like perfectly flat at
The stationary inflection point is when both of them are equal to 0.
Wait, so stationary is when the first derivative is also 0?
Yeah.
Yeah, yeah.
Oh, so that means it's just straight.
It goes like.
It goes like
And then,
like
Yeah, okay.
But yeah.
Oh.
That's, critical points are just important points.
Yeah.
This,
Yeah.
no. That's why
What if it goes concave up to concave up? Is that even possible?
Isn't that just like a parabola?
Like a like a sine function, but like.
What?
Yeah, let's
A
blow it
cosine
from
function?
here.
You got it in the board.
Never mind.
it's okay. It's okay.
Sine functions have normal.
No, not a
inflection
sine
points.
function. Like when you
Yeah.
The functions have
Yeah.
Anyways, so you see how at before the inflection point here, my graph seems to be it's going to infinitely go upwards, right? But then it kind of turns around, and then after the point, now we see, even if we're going up, we see we're slowing down, and then ultimately we reach a point and we go down as well. So that's when the trend changes. When f prime of x is equal to 0, the turning point is when the graph actually turns around. And the inflection point is where the graph, the fate of the graph changes.
Is there a way to find inflection points just from using your calculator?
This is
I think you have to differentiate at least once.
Yeah.
for the paper 3 question.
Yeah.
It was really obvious since they showed us like multiple graphs with the same trend, like the same equation. But in questions like that, we would still have to prove that 0 would be the inflection point by doing this, right?
I haven't done the question.
Yeah, I think you do. I think what you have to do is like just make sure it's found y-intercept and the inflection or whatever point it was. Just always find the y-intercept and then do this twice. Yeah.
Okay.
Thank you, Mr.
Can we move on? I haven't done the question yet, so I can't really explain it. But anyhow, so let's move on to the last part of the differentiation, the implicit differentiation. So this basically happens when you have the variable y, it's already like there as well. So let's say we have y squared plus x, 2x is equal to 1. Let's say we have this weird relation. So by the way, for implicit differentiation, usually you have the case of just relation style, not a function ultimately, but when you have the relation. Basically, what you do is you try to differentiate both sides with respect to x, usually. And then we just have to be careful that y is just a function of x, right? So then when we take the differentiation, we have to use a chain rule. So that's a chain rule to be used. So if I do this work, it's going to become like
2y dy.
2y, and then I multiply by the dy over dx plus 2 is equal to 0. So after that, I can isolate the dy over dx, or I can isolate the y, or I can solve some equations if I happen to know the dy over dx or specific points of x and y.
We take the derivative of both sides.
Yeah, with respect to.
If it was like a kinematic question, would you differentiate against time?
Yeah, usually, yeah. Differentiate by time is the easiest method. There was one person who wanted to differentiate it with distance.
Make everything differentiate by time, then it becomes easier.
Yeah.
Would we usually make it like dy by dx equals something?
Yeah.
Yeah.
So this.
Or it depends on the question. Like at this point, we already kind of all know the y, dy over dx, and maybe you have an x as well. If it was like 2x squared, it would have been a 4x, right? Then if you're trying to find what is the gradient or what is the instantaneous rate of change when x is 1 and y is 2, for example.
Yeah.
Or if the instantaneous rate of change is, let's say, -2 and x value is 5, what is the value of y? It could be like that too. So it depends on the question. Okay. Anyways, so these, all the tools, differentiation, the rules and such, these are helpful. So if you want to differentiate some stuff, that's good. If you want to use your calculator, we can just obviously just graph it, and then you do d over dx, and then select the x value. You can do that. Pretty sure you can do it without the graphing part too, but those are some graphical methods to differentiate as well. Okay. The only problem is that you can only find the differentiation at a specific point, not the entire expression. So for the expression, you have to do it yourself manually. For that point, you can use your calculator. Okay.
Yeah, you don't have to graph it to find a derivative at a certain point. It's just math and then n-deriv.
Yeah.
You define the variable.
Anyways, let's move on. Any questions about the differentiation?
It was solved for derivative.
It's just
All right, let's move on to integrals. So first of all, integrals is basically the other way of differentiation, right? So sometimes we call it the anti-differentiation because basically we're just going backwards. So immediately we can think about the formula booklets. And so there's a separate section for the standard integrals, like these ones and these ones here. What I like to do is I just like to look at the list of differentiation, a list of standard derivatives, and you just go backwards, and that's what you get, right? So if you integrate the negative side of x, your result is cosine x. If you integrate whatever x, you get a ln x. Or if you integrate, let's say, a to the power of x ln of a, then you get a to the power of x. Right? So I think that's a bit easier methods to do. Instead of you don't have to memorize, you don't have to like look at different sections. Right? That's my opinion. But we just have to think about the difference between. Let's talk about the integration by substitution in parts later. We just have to know the difference between the definite integral and also the indefinite integral. So what is the idea of the definite integral? Definite integral is when you have the a and b value. From this point to this point, you want to find the integral, right? So it has a shape like this. Okay. And what happens? Well, what I will do is first I will try to find the integral of my f of x. Let's say the integral of f of x is found by doing uppercase f of x. Then you will take the f of b, or we can write it as f of x with a box like this, BA. So then we can take it as f of b minus f of a. I think that's called the fundamental theory of calculus.
Which one is the bigger number, A or B? Like which one is
A.
A is a smaller
Smaller,
number,
sorry.
b is a higher number.
Okay.
We go from bottom to top. Just like the sigma notation, we go from I equals 0 to n.
Makes sense.
So that's the definite integral. The indefinite integral is basically the similar thing except when you don't have the a and b values. So this one, we're just finding the expression of the integral. So we'll just leave it as uppercase f of x. The only difference here is that we need to add a little constant. That constant is called the integral constant. Because if you think of it backwards, let's say you differentiate this, f of x plus c, then you get the original lowercase f of x, but that c is just gone, right? So we never know what happened to that c. So this is like a unsolved mystery, right? The c could have been like plus 100, but overall it does not affect the lowercase f of x. So that's why we have to add this plus c integral constant. And of course, we'll see in future, sometimes the question kind of gives you the initial condition, which is tightly related to the integral constant, such as if, like, integrate this if the f of x is, f of 0 is 1, for example. This is the most common case.
And the reason why we don't put the integral constant on a definite integral is because it cancels out from f.
Yeah, exactly. It cancels out anyways, so you don't have to. Like, for example, if I added the integral constant on the definite integral, it would have been uppercase f of b plus c minus uppercase f of a plus c. So a c minus c cancels out anyway, so we don't have to. All right, so that's the difference between the definite integral and the indefinite integral. Now let's talk about the substitution. So we always get confused whether to use a substitution or by parts, right? So first, integration by substitution, basically what we're trying to do is, let's say we have a case of you want to integrate, let's do an easy one, shall we? Let's have like x multiplied by 3x squared plus 1. I don't know. You wouldn't want to do the substitution here. Let's say you have a case like this. So integration by substitution, you can think of it as it's a backwards of a chain rule. Okay? If you ever want to undo the chain rule, we use the substitution. So in this case, I know that that the substitution is useful because one, I see a complex expression. Okay, that's my first train of thought. And then my second train of thought is that two, there is a derivative of 1 outside, living there. So in this case, I know that there's a complex expression 3x squared plus 1, but I also see that there's an x, which is a derivative of 1, or
What do you mean derivative?
let's say it's like this.
Okay.
Then it's more obvious, right? Because if I derive 3x squared plus 1, it's going to be 6x.
Oh,
So it's right there. It's waiting for you to be, please, eat me, kind of thing. So then you take this. What? It makes sense, right? So then here, if let's use the substitution u. I'm going to always choose the u with the complex one. And then I take the derivative of this, d over dx is equal to 6x. What I like to do here is I just kind of like to isolate dx. Isolate du. So I'm going to write it as du is equal to 6x dx. Then you don't have to. It doesn't matter. But now you can write it as u times du. Right? My 6x and dx is replaced by du, and my 3x squared plus 1 is replaced by u. Now we just have an integral of u, and that's it. U, which is just u squared, 1 over 2. So that's going to be 1 over 2, 3x squared plus 1 to the power of 2.
If it was x, what do? You do 1 over 6.
Yeah,
right?
you have 1 over 6. Or you can just bring out the 6 outside.
So in the beginning you said you wouldn't use integration by parts or substitution on this. What did you say?
This one, substitution is useful. Because, 1, there's a complex expression, and 2, there's a derivative of that complex expression outside, visible. So if you know what and how to use a substitution, it's really obvious. It's kind of it's literally waiting there, to be eaten.
It's very easy.
Yeah. And it's also it's obvious, it's visible.
Is it always visible?
It's pretty visible.
It's pretty visible.
It'll probably be in 2 different brackets too. But
Yeah. All right, so that's the case of the integration by substitution. I think integration by substitution is a lot easier than the integration by parts,
yeah.
except you don't have that in your formal booklet, right? Let's look at the integration by parts. Luckily, you have that in the formula booklet. As you can see here, u dv over dx. First thing that you have to do is you need to choose what is the u and what is the dv over dx, or what is the v prime, right? Let's try to make I'll try to bring an example question, right?
Wait, so if it is a function multiplied with the derivative of another function, we use this.
For the integration by parts?
Substitution.
No, for a different function. Is that it? Am I understanding correctly?
I found a good example.
Wait, say it again.
So if in the integral there is a function and it's multiplied by the derivative of another function, we use this. We find that other function.
Different function.
Like it says dv over dx. What is dv? Yes. I think-
Okay, can I try to explain?
Yes.
So we use the integration by parts. Well, obviously, if you look at this, can I use the integration by substitution? No, because there's no one specifically, this is a complex one, and there's no, even if I say that cos x looks more complicated than x, but then derivative of cos x is not x, right? So this is not possible to do with the integration by substitution. So then what do we do? At least you have to use the integration by parts. Then we look at the formula booklet. So I see that I need to choose one to be u and one to be dv, like, or v prime. And then I see that, hey, I have to quickly find the v, which means that I need to integrate v prime to v. And I also need to take the u and I need to find the du over dx. And hopefully when I do that, ultimately my du or u, if I differentiate it multiple times, it's ultimately gonna disappear. Right? That's my end goal. So then, let's try to find what is u and what is v prime. What do you think? What is a u and what is a v prime here? I think obviously v prime will be the cosine of x, and the u will be the x. And then at this point, I think it's also easy if you try to find the u prime as well. U prime is 1, and v is also quickly sine of x. Right?
What's like what tip do you have for determining which one's u and which one's v?
Yeah. So first one is that u is easy to differentiate. And 2, v prime is easy to integrate. And 3, u after multiple differentiation becomes constant. Or in short, u should be a polynomial. Anyways, after you do that, we follow the logic. We use the uv minus v du, integral of v u prime dx. So what is that? uv is x times sine x, so x sine of x. And then v du, v is v is sine of x, and u prime is just 1, so it's just this. So that's pretty easy, right? And it becomes x sine of x minus plus cosine of x plus c. Okay. If you want to explain, integration by parts is kind of a result of a product rule, but that's, if you want a bit more complicated, you can see that.
What did you write on the end there, the number 3?
Or u after multiple differentiations becomes constant.
Oh,
This not become negative cosine of x or not? Why is it cosine of x?
Integral of sine of x is negative cosine x.
Okay, because I'm stupid, because there's another negative.
Anyway, so that's the integration by parts. Sometimes you'll do this, and then you do it one more time because you see how we have to do another integral. And sometimes, let's say, like you have another x lingering, and then you have to do this again. And then sometimes you have to do this infinitely many times. Then what you do is after like couple rounds, you kind of go back to the original case. Like let's say you do this one more time, and then you get x cosine of x dx. At that point, we can just rearrange this thing. Like it's an equation overall, right? So you rearrange things to get rid of the integrals, and then divide it by 2, or things like that.
If you see like trig with integrals, it's usually by parts, because they make you do it twice, and they put it. You find this. You do the parts twice because you get something like x sine x, right?
Interesting. Is that the pattern
It's
usually?
yeah, like for like all the
Cool.
textbook questions I did, it was pretty much all of them were by parts.
Yeah. Or like each part of x, even.
Yeah,
right?
yeah, that too.
That one's just one round, and you immediately know it too. Anyways, let's move on. Okay, kinematics. So, kinematics. Now we talk about kinematics. Now that we know what is going on with the integrals. So in kinematics, we have 3 parts: the position, or let's use displacement, and then we also have velocity, and then we also have the acceleration, right? So from displacement to velocity, as the kind of the unit implies, if you differentiate this, if you differentiate with respect to time, it becomes velocity. And then you differentiate this one more time with respect to time, and you get acceleration. What about the other way? Well, if you integral with respect to dt, then acceleration becomes velocity. And then you repeat this one more time, accelerate, integral with respect to dt, then you get the displacement. So you have kind of a chain going on here. Displacement, velocity, acceleration, or acceleration, velocity, displacement.
Do we ever have questions that require us to calculate the jerk?
No.
The derivative of the acceleration. That's called the jerk.
It's sure.
Yeah,
I've never heard of that.
that's
I've
the
never
that's the
heard of that.
physics term.
Really?
Really?
It's weird.
Yeah, like when your car just
Isn't
goes
it-
forward, that's like a jerk motion, right?
And it's like pop, and then
It's
so
like a
on.
change in acceleration. It's called jerk.
I think some nerds are talking. Let's move
All
on.
nerds here. Should
Well, okay, so these are the displacement, velocity, and acceleration. But what if you have like a distance, right? What if you have like speed? The thing about the displacement and the velocity is that they're vector values. So the direction does matter, right? But the distance and the speed are scalar values, which means that the direction does not matter too much. Then also the thing is that for distance and speed, it's always going to be positive. So then what do we do? Then I think it kind of automatically leads to the next part about the graphical part, or geometric part. Geometric analysis. So what we mean by this is, hey, so what does the integral mean overall, right? The derivative, what is the meaning of derivative? We find the instantaneous rate of change. Then what is the meaning of the integral? Integral is about finding the area. So when you have a function like this, and then we have point A here and a point B here, then if you find the integral of this f of x, what we're going to do is we're going to find the area underneath the curve. So that's what it means by the integral. So this is integral of f of x dx from a to b, right? So if there's a question asking you, hey, find the area under the curve and above the x-axis, then you just do this, right? So you can do this on the calculator using the second calculate, or you can just do the math and then you can integrate with the values that you see. The only problem here, only twist is, hey, what if you want to find the area underneath the curve as well, right? Then what do? Well, the problem is that we're only going to calculate the top side as a positive, so you have to be a bit more careful, right? So let's say we have like a shape of a graph that goes like this, and then you want to have a line here, and then you want to find the area of this plus this plus this. Right? So what you can do is you can either break it down into three pieces, like A and then B, let's say. Then you find the integral from 0 to A, and then you add it to integral from A to B, but it's negative, so we put it to positive. And then we add it to, and then we also add integral from B to, let's say, C. So we do it by three parts. Or we can take this f of x, and then we can make it an absolute value of f of x, which is going to make the function always positive. So it's going to look like this, this, this. Then you take the integral, and then you can also find the area.
Can you show how to find area when it's on the y-axis?
On the y-axis, sure. Yeah, we'll talk about that in a second. So these are some methods of finding the area. Also, if you want to find the area between two curves, you can do that too. So let's say we have f of x here, and then we have a g of x here. Basically, if you want to find the area between these 2 points and these two curves, then basically what you do is you find the area under the f of x, and then you subtract the area under the g of x. So basically you do the whole minus parts situation. So you do f of x minus g of x dx. Or if you want to be smart, you can just combine them into one, right? F of x minus g of x d of x. It's either or. It's whatever you choose, whatever the easier one you want to go with. Yep.
And when we use our graphing calculator, if we use the one on the bottom left,
Yep.
does it take it as a vector or a scalar, or is it like, does it give you just the area, or does that go forward, backward, and forward?
It's gonna give you the negative value, so the sum will be not the area that you're looking
Not the total.
for, not the total. So that's where we use the idea of the distance and speed, right? So if you want to find the displacement, then it will be like different, right? It won't. Will be. Let's say you move from the middle to the left and to back in the middle. The displacement is 0, so it makes sense, right? You're treating the bottom side as negative, that's fine. But if you want to find the distance, then you want to include that distance, how much you move here and how much you move here, right? So then you want to go the positive side, add all the areas separately into sections, and then you get the speed. Same thing for velocity and speed with respect to the acceleration. Okay. And then of course we can take this a step. I can give it a twist here by trying to find the area between the y-axis and then the curve like this. Let's say. So what I like to do in this type of question is I like to just find the inverse of it. So then when I pick the inverse of it, it's going to look like it's going to look like this, right? And then we can have the a and the b value like this. So how do you find the inverse? You take the function and then you do y equals that, and then swap y and x equals that, blah blah blah, and then you isolate the y variable, and then you have an inverse, and then you use the same points, and the life is fixed.
What happens to A and B?
So the problem is that in this question, they're not going to give you the a and b value like this, right? They're going to give you these values. So then after you find the inverse, or just by looking at the a and b value, you plug in f of a to get this point, f of a, and then you plug in, you get f of b, right? And then you can use these original f of a, original f of b values.
So the y values of that are the x values of this?
Yeah, after you take the inverse. I think that's the easiest strategy that I can think of. Most consistent one.
So, just say X.
Okay. And of course, we take this a step further for our HL stuff, is when we try to find the volume. So what we do is we take a function, and then let's say we have a function like this, and then we rotate it around. We rotate around from this point 0, let's say, to point B, and then we take a rotation like this. And then what do we do? Basically, what we're going to do is for each height, that we're going to consider that as my radius, and then I'm find the area of that circle or disk, and then I integrate it. I add it from 0 to B, right? So that's what's going on with the volume of revolution, right? This is the volume of revolution. Which, luckily, is given in the form of a booklet. So we have it as V is equal to, from A to B, what is it? Pi y squared of dx. So basically what we do is we have the y, which is the f of x, we square it as a radius, and then we multiply by pi to find the area of that disk, and then we integrate that from A to B. Okay.
Why is just f of x?
Wait, why is it y squared?
Y represents the radius.
Which is just that.
It's just like
It's a
pi
function,
squared.
right? That's just a
Yeah,
function, right?
f of x.
And you put pi on the outside because
Sure, yeah.
constant.
Okay.
Okay.
Same thing for the volume of revolution. About the y-axis too. It's just the other way. Same thing. Okay. All right. Any questions about the geometric interpretation?
In the formula booklet, it says area of region enclosed by a curve and y-axis, and it's like the absolute value of x for some reason. I don't get that. So, what does that mean?
Isn't it when it's below the what?
Yeah, that's what I was thinking, like,
By
when you
the-
took the absolute value.
By a curve and at y-axis though.
Now y, yeah, that's why
Yeah.
I'm confused. That's the x-axis. Oh, it's differentiated by like in respect to y. That's why.
Oh, yeah.
Okay, that makes sense. So we did take it the inverse.
Okay, self-explain. I think like when you take the absolute value of x, remember what happened to the absolute function of that? Like the f of x is the bottom side both positive, right? Whereas the absolute, like if you graph f of absolute value of x, it's actually not like that, right? We ignore whatever on the left hand side. We just graph the right hand side. We just reflect it on the other side, right? So I think we are only wanting to look at the right hand side. I think that's what we mean by absolute value of x. We only want to look at the right hand side. So in this one, for example, like we only graph the right hand side and we just want to look at the right hand side.
Yeah.
Right? Similarly, like how, if we find the area under the curve, we're automatically just looking at the positive side of the graph. So I think the idea is similar. Does make sense?
How do you find the area of the y when like the graph is under the x-axis?
So like I said, what you would do is you take it into pieces. So if you want to find the area between A and B, right? Then you find the area and then we multiply by -1.
But how do you know what part is like under once it's inverse?
Inverse?
Like if some of the when it's around the y-axis, if it's under the x-axis, how do you know what part of the graph is going to be under the x-axis when you inverse it?
addition of limits, right?
What do you mean addition of limits? Like actual addition.
This with limits, right?
Sorry, I don't really understand.
Like the thing on the left,
I'm just trying to
if that's
use-
under the x-axis,
I'm just trying to make
when
sense
you
of
like
these
flip it, so you can.
But are you talking about the inverse one?
Yeah, the one that's around the y-axis.
Yeah, yeah.
If it's like below the x-axis,
Yeah.
and then when you flip it, how do you know what parts are going to be below and above the x-axis? So like what?
Project it on the 2D area. Be like this, right?
Well, if it's on the right hand side of the graph, it's always going to be above the x-axis, right?
Sorry.
Pi r squared over
Yeah, pi squared too, right? And then what you're doing with, so that's what.
Yeah.
That's
Like
so
this?
pi
Yeah.
squared
Mhm.
over
And then you want to find the area
two.
from
In the 3D shape.
like
Here.
here to here.
Yeah.
360.
You want to find this area?
Yeah, I understand how to use it. This is for.
Well, if you find the inverse of it, it's going to be like
This is for wrapping around the
like this, right?
I'm just trying to understand the math.
So you don't have anything to worry about in the first place.
Oh, so it doesn't actually becomes negative.
Like this. So it's always positive anyways.
So the inverse is always above the x-axis.
Well, as long as it's a, like.
As long as the curve is on the right hand side of
Yeah.
the y-axis.
Yeah.
Oh. So they won't ask you to like find the area when it like keeps going to the left of
I
the
just
line.
learned that in kinematics.
Well, in that case too, first we first find inverse, and then you treat it like the question above. If it's above, that's positive. If it's below, you multiply by -1 to make it positive.
And
Okay.
X and Y, okay.
Does that make sense?
Yeah.
Once you find the inverse of it, you can treat it like a regular area under the curve question, right? So at that point, if it's above or below, then you can reconsider.
Yeah.
Like if you like.
Anyways, okay, I think we're done with the integral part. Can we move on? We're already over 1 hour mark, so I want to get going. The next two parts are you could say they're harder or easier. They're the differential equation. Okay. So when you have the differential equation, first thing we should consider is that we have the initial condition So what is the initial condition? Initial condition is when, like they're giving you like f of 0 is equal to 1. So then when you have a plus c, that plus c is resolved at some point. Anyways, other than the initial condition, there are many ways to solve the differential equation. The first method is the Euler's method. Everyone's hatred.
It's useless.
But it's in the form of a booklet and it's in the curriculum, so yeah, you have to know.
I've never seen it in like a class exam.
Because it never has been.
Which one?
Which means that you have a higher chance that it's going to be in this year's exam.
Exactly, that's what I was gonna say.
No.
So I think the Euler's method.
I still don't know what it is.
Okay, so basically what you're doing is you're trying to find the a function, and then you have the initial value, right? At f of a, let's say at a, you have f of a, right? And then you use the differential equation as a hint to guide you. Okay, so you don't know what next value will be, but you know the f prime of a is that point. So then you know that, hey, this is my differentiation. This is my rate of change. So let's go this way. And then after I go some steps, each step, let's recalibrate. So then you find another derivative, and then you go up by that much. And you find another much. And then you find another much. And then find that much. And then hopefully by the end, you'll be able to solve the differential equation using the step-by-step method. So basically it's lots of recalibration with each step being h steps long.
Is this the equivalent of just drawing like rectangles under it and then finding the area?
No.
That's the integration version.
Riemann sum thing. So yes, it's kind of similar, but not exactly the same. Euler's
This is
method
more accurate.
is for the solving differential equation. So this one, we have the purpose of solving equations. Whereas Riemann sum, which is kind of like this, that one is we're trying to find the area under the curve. Okay. But yeah, the method itself is, you could say that it's kind of similar because we're taking infinitely small steps infinitely many times.
Did you ever use like Riemann sum on the questions?
Maybe, but I don't think it's really the main focus here. Euler's method though, yes. But I think it's not, what I suggest is we try to make a table out of the Euler's method, right? So what I try to do is, hey, for the h of 1, or for n equals 1, like it's this. And then you do 2, and then you do x, you update the x value, you update the y value, and then you do it again, you do it again, you do it again, and stuff like that. So if you make a table for the Euler's method, I think it's quite helpful. Okay. So that's the first one. That's kind of a brute force method, right? And then we have some more sophisticated methods later on. The first one being the separable differential equation. What we mean by the separable differential equation is that whatever expression you have, let's say dy over dx is equal to, let's say you have like, let's use f. All right, let's use y, sorry. Let's say dy over dx is like y times x. So it's separable because we can, divide some sides. I can do some maneuvers. And what you want to do in the separable differential equation is you want to put the y on the left. And put x on the right. So you want to take this and say, hey, this is going to be 1 over y, dy over dx is equal to x. So it's separable because you could do this. If you cannot put y on the left and x on the right, that is not separable differential equation. And then you do the integration, and then it becomes 1 over y, dy is equal to integral of x and dx. And then you proceed further.
You differentiate both sides by dx, and the left side dx is cancelled out. Is that what's going on?
Integrate both sides.
Integrating.
yeah, with respect to dx kind of thing.
Okay, that makes sense.
So that's the idea of the separable differential equation. Any questions about this one? This one is an easy one as long as you just know this strategy of putting y on the left and putting x on the right. Okay. And the next one is the homogeneous equation. So for this one, we have to use the substitution. Y equals Vx, where V is a function of x. Okay. This part is the part that people will forget, right? So be careful. V is a function of x. So V is just going to be y over x, right? So this is used when you have like dy over dx is equal to f of y over x. This is homogeneous one.
Now I get it. Okay.
So for example, let's say we have a function like this. Dy over dx is equal to, let's go easy, y over x squared. Let's say. Then using the substitution, we know that y equals vx. So then we're going to take this, the first one, and then differentiate both sides with respect to x. Right? So then it's going to be, left hand side will be dy over dx. We're doing the implicit differentiation, dy over dx. And then the right hand side is vx. Vx is not a v is not a constant, right? So it's v is a function of x, which means that we have to use the product rule. So it's going to be v prime or dv over dx
It's just a function that has x. Like 2x plus 1. It's just
plus
an
v.
So is it there?
Sorry, what are we doing?
What are we doing?
We're differentiating Vx.
Yes, we're differentiating vx, and knowing that a v is a function of x, we can't just be like v is the answer, right? Because so we have to use the product rule. So I used the product rule. I differentiated the v, multiplied by x, plus v's alone, and I differentiated x, which is 1.
Yes.
At this point, what do? I replace dy over dx on the left hand side with dv over dx times x plus v. Equals, what about the right hand side? Y over x is v, right? So it's going to be v squared. And then let's do some maneuvers. dv over dx times x is equal to v squared minus v. And then now, this is kind of a separable differential equation, right? So let's put all the v on the left hand side. Let's put all the x on the right hand side. Then we have to go like 1 over v squared minus v, dv over dx is equal to 1 over x. Then, if you can try to do 1 over v squared minus v, dv is equal to 1 over x dx. And then you proceed to solve. I think you have to use the partial fractions for the left hand side. So you could say that homogeneous differential equation is kind of like it's a separable differential equation, except it has a bit of a layer outside. So you have to pop that balloon, and then now it becomes a separable differential equation. So you do that. Okay. Any questions about the homogeneous one? Just key parts once again. V is a function of x. If you remember that and the y equals vx, then I think the process is. Good luck memorizing that. There's no hints on the formal booklet, so. I have a great guest. Number 5, fan. You need to make a phone call. Anyways, let's do the last part. Integrating factor. So, last part is the integrating factor method. So luckily, finally, we have the formal booklet to help us. So apparently, integrating factor for y prime plus p of x times y equals q of x is each part of p of x dx. So let's try to just interpret this. So what it says in the formula booklet, what it means, what was it here? Y equals q of x. And then we basically have each part of integral of p of x d of x, right? So what this means is, it's I of x. Okay. So your first part, if you encounter an integrating factor differential equation, is to identify the p of x, and then you do integral of p of x and make it each part of that. And that is your I of x. After you find the I of x, you're going to multiply both sides by I of x. So it's going to look like I of x times y prime plus I of x times p of x times y is equal to I of x times q of x. Okay. After, you will usually be able to do some work here. Is that our goal is to say that, hey, this is an outcome of a product rule. So you can actually simplify the left-hand side. Should I do an example here as we're going this?
Because I don't get it.
Yes. So basically, at this point, because we know that the left-hand side is an outcome of a product rule, then we can just simplify this as a d over dx of something, and then we solve the differential equation. Okay. Let's do an example one.
It's weird. Like,
What is IX? That's what I don't get.
Ix, like you see in the formula, it tells you, right?
yeah.
It's e to the power of integral of px.
I don't understand how
never
to
saw
turn
this.
make this solve the left hand side.
11 days.
Yeah.
That's a lot of days.
Oh, it's math or physics, huh?
Yeah.
She knows it.
Well, 11 days till the math exam. That's what we're saying.
Okay, let's try this one. So for this one, so I think what I'll try to do, like at first it doesn't really look like the basic pattern, right? So I'll have to divide it by x on both sides. So it's going to be dy, let's use y prime to match everything. Y prime plus 1 over x y is equal to cosine of x. Let's see. So I know that p of x is 1 over x and q of x is cosine of x, right? So now let's try to find the I of x. What is my I of x? According to my formula booklet, it's going to be e to the power of integral of 1 over x dx. Right? And at this point, when you integrate that, you don't have to do the plus c. Well, what is it? It becomes e to the power of ln x, right?
Why do we not need to do the plus C?
For some reason.
We'll have to we'll worry about the plus c later on, anyways. I think that's the logic.
Okay. Yes.
So what is the e to the power of ln x?
Right.
Obviously.
Yeah.
E to the power of ln x is just x,
Silly
right?
mistake.
So then I of x is just x. So now let's multiply both sides by x. So now it's going to be x y prime plus x times 1 over x. And naturally, most times, the I of x and the p of x will cancel out.
Okay.
Not entirely, but somewhat cancel out. So it's just going to be plus y equals x cos x. Wait.
How did we get there?
We just got the same thing over again. Are we looped inside forever?
Because it's ln x.
Why did we make the I of x again?
And why
So you can multiply it to every term on left hand side and right hand side, and it solves somehow. It magically gets better in other questions.
Right.
Yeah.
Right, I get that.
Measure gets better than what?
Like what you have to do is like the left hand side would be like it's like a product rule, right? So you can simplify it and just like crunch it in, and then it just becomes easier for
I
some reason.
remember, yeah, I forgot.
And the e to the power of ln absolute of x, why did that got out as x? Not
Because
absolute.
e to the power of ln is
That must be absolute.
Okay, so
It
believe it or
takes-
not, we're kind of getting there, kind of. At least we took one round, and if you can get out of it at this point, that's fine, right? So remember that the left-hand side, we know that we should be able to represent this as a product rule of something. So it means that we should be able to say that this is d over dx of something. Can you imagine that what that would be?
No.
Yeah.
After some
Oh, yeah.
brilliant mindset, you can say, hey, d over dx of xy is going to result in xy prime plus y.
Oh, it's
It's a product rule of something, right?
So do we even need to do the integral factor?
Probably not.
No.
But it's a good practice, right? And then what can we do? I think we need to now integrate both sides. So it's going to be xy is equal to integral of
That's integration by parts.
x cosine x dx. But yeah, you get it, right? So you integrate by parts on the right hand side, and then you isolate y, so you get y is equal to blah blah blah, everything x. Okay? So that's what I mean by, so once going back, we have this weird thing, differential equation, and then we find the integrating factor, e to the power of integral of p of x dx. And we multiply both sides by I of x, and then the left hand side, we try to find that as d over dx of something. Usually, of course, it'll involve some kind of y and some kind of x. Okay?
Not really.
Can we find an example that actually works?
Sure.
Please.
Another one.
I don't calculus. This is funny.
They usually tell you though, in this kind of question, they tell you like what to use.
Oh, really?
Yeah. They're nice.
IB is nice.
Well, okay, they won't tell you if it's like how you solve the, like they won't tell you integration by parts or substitution, but they'll probably tell you about this.
Okay, so same thing for this one. Let's rewrite it in the order that appears on the formal booklet. So once again, I see dy over dx is not alone, so I don't like that. So let's put it as y prime plus x plus 1 over x, y, is equal to 1 minus x. Right? So I divided both sides by x, right? And then I says find the I of x. What is the I of x? It's e to the power of integral of p of x d of x. What is my p of x? My p of x is going to be integral of x plus 1 over x of d of x, right? And what is this? It looks complicated at first, but I think we can split this into two parts. It's going to be 1 plus 1 over x, right? So it's going to be 1 dx plus integral of 1 over x dx. So then there's going to be e to the power of x plus ln of x, right? So then we can think of this as e to the power of x times e to the power of ln of x, which is just x ex. Does it make sense? Knowing that, let's multiply both sides by this integral factor. So it's going to be x ex y prime plus x ex is going to be ex x plus 1 y is equal to x e to the power of x times 1 minus x. Okay. So once again, my goal is to try to find the left hand side as a multiple of a product rule. Let's try to find that d over dx. I'm kind of tempted to divide by both sides by e to the power of x, but then I realized that it'll just become the same thing once again. Does that happen for every single time?
No, well, that's because you multiplied everything by e to the x. Of course, if you divide by e of x, everything is going to go away. Of course, that's going to happen.
Okay, so I'm doing fine, right?
Yeah.
So then, okay, what's going to be? Well, first I know that it's going to have a y somewhere in the ingredient. Then what's the other one's going to be?
Yeah.
I think it's gonna be e to the power of x.
But you need the x to come down.
Hmm.
We need x.
So that's a what rule now? It's a product rule, right?
Yeah. You need something more than y. Where is it?
Mm-hmm.
Shouldn't it be just x e to the power of x if it's just as straightforward?
Should I try to like simplify a bit more here? I'm tempted to do something like this. Can I do something like that? You think? Probably not. You know what? I want to go home, so I'll just show you an example that it works. You have an
Is
idea?
it x plus 1? Yeah, no, it's just x e to the power of x times y.
Sorry?
I think it's just x e to the power of x times y. Because,
Because the x comes
yeah, x times e to the power of x, the derivative of it is e to the power of x times x plus 1. It simplifies to.
Just like this?
No, there is an x in the
Here?
in the front as well. Yeah, I think so.
But then wouldn't you want to do product rule of x e to the power of
No,
x?
because if I was just looking at the product rule. If it's just a straightforward product rule, the part that's multiplied with y prime
Yeah.
is gonna be just x.
The same, yeah.
Right.
Yeah.
So if you just put that, and if you just find the derivative of x times e to the power of x,
Yeah.
it becomes e to the power of x plus x times e to the power of x, right? So you factor out the ex, so it becomes ex times x plus 1.
Oh.
So it's just,
So it just works out.
yeah, it just works out. No need to say.
Okay. So I've been thinking about it.
Do that everything.
Difficult for no reason.
I think that's what for every integrating factor, the coefficient, right, you can't really call it a coefficient, but whatever's attached to the y prime,
Yeah.
uh,
It's always gonna be like
the
that.
thing times y. I think that's pretty much always what it's gonna be.
Cool. All right. Okay. I'm happy. And then we integrate both sides finally. So then we get x e to the power of x y is equal to integrate of, I think we can expand it here, right?
Okay.
So let's do x e to the power of x minus x squared e to the power of x. Then we magically do that. Right. And then I think we can do it. And then we divide both sides by x e to the power of x, and then we get the answer. All right. Should we move on? I've been sitting here for an hour and 30 minutes.
Yeah, I already gave up. Yeah, this is
We
like.
still have McLaurin's.
We have
Yeah,
McLaurin
we
series.
lost one.
Although McLaurin series, I'm pretty sure it's a lot easier than this one.
Yeah.
Oh, yeah, I was.
Prawn,
gonna
don't
ask
give
you
up.
this.
It's fine. We're still in this.
Sure, I wanted to ask you this. How do I how do we recognize which method to use? Do we just solve a lot and try?
Sometimes it tells you.
What-
Yeah. So once again,
Gives you
no,
hints.
Pray to God.
no. So first, you use the integrating factor method if you notice that pattern. If you have the y prime plus y plus something y equals something, that's immediately that's easy to notice, right?
Yeah.
And also it's on the form of booklet, so that's easiest to do, easiest to find.
Don't use Euler's method.
Yeah, exactly.
And if you see if you see the y and x could be separated, which means that y and x are somehow like multiplied together or divided by together, that's when you use the separable differential equation.
And when there's y.
If you can
over
clean
x.
cut y and x, that's separable. If you have some kind of y over x, that's when you use the homogeneous. Or sometimes it's just easy. You don't have y, it's just everything is x. Then you just integrate everything, that's fine. That's the simplest one.
You don't even call it a differential equation. Wait, how do you get the y from that then? If you have no.
If you integrate dy over dx with respect to dx,
Oh.
then it's, with both sides, it's integral of dy. And on the right side, it's differential. Integrate with dx. So you get y from 1. Y is born out of nowhere.
Maclaurin series.
All right, Maclaurin series. See, I only put like two parts here. Okay? So basically, what we do is Maclaurin series is we just follow the formula. So sometimes we can just use the special functions. We can follow it, or we can make our own. Right. So we have f of x, and we can represent it as f of 0 plus x times f prime of 0 plus x squared over 2 factorial of f double prime of 0, and plus dot dot dot. Right. So Maclaurin series, the condition is that f of x or d over dx of f of x is easy. That's a condition. Right? You have to find the differentiation of f of x pretty easy.
That'll be 0.
And then, and even if it's kind of complicated, ultimately you put f of 0, so then your life is simple.
Can you
A lot of the x's were
You can
cancelled.
put f of 0 first and then derivative it. Can you?
I don't think so. I don't think you can. Okay. Or you use the formula. And then what do? We and also it's gonna ask you to find like a specific term, right? So then we can just look at the formula and be like, hey, if we're looking for the coefficient of x squared, then we're just gonna look for the f double prime of 0 divided by 2 factorial. If you want to look at the coefficient of sine of x, let's say coefficient of x power 5, then it's just going to be 1 over 5 factorial, right? So for example, when you have like a weird function like sine of x, cosine of x, then we can just say, hey, sine of x times cosine of x is just x minus x cubed over 3 factorial plus x power 5 over 5 factorial, multiply by 1 minus x squared over 2 factorial plus x power 4 over 4 factorial. So now it's kind of like a binomial distribution, a binomial theorem kind of thing. So you multiply this expansion, and you multiply this expansion, this series, and then you merge through a lot of FOILs to find exactly what coefficient we're looking for.
Is there a general formula for this?
No.
Yes, there's a general
Yeah.
formula. F of x is f of 0.
Not when you multiply.
So then it's going to usually ask you, hey, what is the coefficient of, let's say, x power of 4 term? And you're going to find that, and you can just kind of like do it faster by cheating. Like, okay, so x power 4 is, found by doing x power 4 times x power 0, x power 3 times x power 1, x power 2 times x power 2, and such. So that's another way to think about it. Okay. Why do we do this? Because it's easy to integrate.
Is it? Yeah.
Easy to integrate because, like, imagine doing an integral of sine of x, cosine of x. That's barely impossible, right? But then if you represent this, ultimately, Maclaurin series is a polynomial, right? Because it is a polynomial. A polynomial, we're really good at integrating. Right, I think that's about it for Maclaurin series.
What's
And we're just estimating it, right?
We're estimating.
Well, they say something about like convergence with Maclaurin series. What do they mean by that?
Convergence of the Maclaurin series.
Or maybe not convergence. Some
It is convergence. I think so Maclaurin series only exists for a certain value of n. So usually here I said coefficient of x power 4, right?
Yeah.
So that's gonna be, if I stop at that point, it's gonna be the 4th degree Maclaurin series.
Yeah.
If we're trying to find until the x power 4. After that, I don't know what exactly happens, but after that, the series kind of it starts deviating from the original function.
Okay.
So then we kind of stop there.
And how do we find the convergence?
The class notes for that.
Do we need to know that?
Yeah, it says IB exam loves the word convergence.
What exam?
IB exams.
Uh,
What other exams are we doing?
I don't know.
Oh, limit.
So there's an interval of convergence. For some value of x. Like here, you can see an example in the bottom, right? Explain why the series is only convergent for x between negative pi over 2 and pi over 2. Well, obviously, it's 10 of x, right? It's a cosine, it's a
Yeah.
trig function as a limit.
Oh, because Maclaurin series would go on forever, and there some especially for trig, there's going to be a boundaries that.
Yeah.
We just said that.
All right. I think we can stop there. Thank you for staying around for an hour and 35 minutes. Hopefully this was helpful
Yes.
to